All right. Hi, everyone. Welcome to our first official video lecture. Since it's the first one, I just want to make some comments on how this is going to work. First, above this embedded video, you should see some announcements. These are going to act like our in-class announcements before class starts. So this video, or these videos in general, will just be me talking about the sections. The announcements above are the things that I would be talking about, like what homeworks are due, what things are coming up, etc., etc. Another thing that I'll note is that I'll be posting the unfilled versions of these. So you can see right now there are like lots of blank spaces where we would write things. I'm going to post those online. If you want to copy from those, you're welcome to. I'll put a link to that above, so it's easy to find, but they'll just be probably where you would guess they are in the files folder. The last thing I want to comment on before I get started is, I don't know how long this video will come out, but especially with these initial comments, but my goal is for these videos to be no longer than an hour, and in fact, I want them to be closer to 45 minutes. One reason they're going to go really fast is that, one, you guys ask questions during class, right? And so that just naturally adds time to lectures. And then also, I usually have you guys pause and do group work. And because of how I'm doing this, that's no longer an option. However, there are going to be points today where problems appear, and my expectation is that you pause the video, try to work it out on your own, and then continue playing and see what I do. Obviously, I can't police this in any ways, but it's to your own benefit to get this practice on your own. All right, without further ado, let's begin. So before we were disbanded from campus, we've been talking about solid shapes. We've been talking about things that look like prisms and pyramids and all these different types of solids. In 13.2, we talked about how to find the surface areas of these objects. That is the area on the outside of the objects. In 13.3, we'll discuss the volume. But before we discuss volume, I want to remind you of what area is. So remember that we defined area in the following way. We defined area to be the number of 1 by 1 unit squares in an object. So if I've got, let's say, a 2 unit, let's make it inches, 2 inch by 3 inch, not drawn to scale, object, you already know the area is 6 square inches, but how do we use the meaning of area? Well, we just know that if we have a 2 by 3 inch, well, there are 2 1-inch segments and 3 1-inch segments going along the sides. And yeah, let me go ahead and redraw this so that it actually looks a little bit more right. There we go. And so now I have a bunch of 1 unit by 1 unit squares. And how many do I have? I have 1, 2, 3, 4, 5, 6. So the area of this square, this rectangle, is 6 square inches because of the number of squares. Okay. So that's how we defined area. And we actually did already define volume, but I'm going to do it again since it's been a long time. We define volume in the exact same way. Volume is defined as the number of 1 unit by 1 unit by 1 unit cubes. And I'm going to do a visual demo for this, but just before I do that, I realized I forgot to mention one thing. This will probably be in an email, but I will already be posting the filled out versions of these notes, as well as the unfilled version. So you don't need to feel like you have to take notes, but I know some people would like to take notes. So, all right. So yeah, so area is the number of 1 by 1 unit squares in an object. Volume is the number of cubes. And so to demonstrate this, I'm going to pause and switch to a video. Okay, hello, I am now here. So I just gave you the definition of volume, and I wanted to give you a visual. I've actually shown you guys this visual before. So imagine I've got all these cubes, right? And the way I want you to think about this is, you know, each of these cubes, each one of these, let's give it a 1 by 1 by 1 unit dimension, right? So let's say this is like 1 inch, 1 inch, 1 inch. So the volume of this is 1 cubic inch by definition. We call this 1 cubic inch. And so if I want to know the area of a much larger object, maybe something like this, or I think I said area, I meant volume. The volume of this object is just counting how many cubes I have in this. It's very, very basic. So I can just go through and literally, if you remember, the primitive way of finding area is counting all the unit squares. It's the same thing for volumes in three-dimensional objects. I just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, I've greatly miscounted. Let's try it again more systematically. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, good. There are 24 cubes here. If I was to take apart all my cubes and stuff, I would end up with 24 total cubes. Okay, so that's all we mean by volume, is it's just counting how many cubes fit into our object. And of course, the number of cubes could be a fraction, it could be a weird number, because maybe I have 5 whole cubes and then only half of the cube. We'll get to stuff like this in just a moment. But for now, let me switch back. All right, we should be back now. Okay, so that's what volume is. And our goal for today is to talk about the volumes of all the solid shapes that we've discussed. And the formulas end up being very clean, but maybe the intuition for why they work is a little more complicated. So let's start by talking about volumes for prisms. So if you remember when we talked about the area of shapes like triangles and parallelograms, we had a triangle, and what we did is we picked a base, and then given a base, we needed to find a corresponding height. And we're gonna have to do the same thing. We're gonna have to find the height, except we already have bases for these objects. So the height of a prism is going to be defined to be the distance between the two bases. So, sorry, I don't know if I said this, but we're doing prisms and cylinders right now. So the height for a prism is just the distance between its two bases. So we already know how to talk about bases for prisms. So I've got 3 prisms here. I've got a triangular prisms with 2 triangle bases. I've got a cylinder. So I said I had 3 prisms, I think. I have 2 prisms and 1 cylinder. So here's a cylinder with a circular base, with 2 circular bases. And then I have an oblique rectangular prism. So the bases are kind of like squares here. And of course, these 2 up here, those are right pyramids and cylinders respectively. Okay, so I've labeled all my bases. And so the heights of these pyramids is just going to be the distance from the top base down to the bottom base. And I want the vertical distance, right? So in both of these, the distance goes straight down. Even in here, the point for this oblique prism is I want the height to go straight down so that it goes from the top base down to the bottom base. It's like, imagine you put a measuring stick perpendicular to the floor, sticking straight up, and you just saw where the top base reached. That's what the height is. Some people will often think that this distance right here is the height for an oblique prism and or cylinder, but it's not. We call this the slant length. Sometimes the slant length is useful. We're not going to really use it, but I just thought I'd point it out because it's tempting to think that this is what we mean by height, but it's not. We always want height to be going vertically. All right, and now that we have the height, the formula for prisms is actually really not too complicated. The volume formula is you take the height and you compute the area of the base and of course we have cubic units because we're talking about volumes, and that's the volume. It's actually not too complicated to describe. Whoa, height. There we go. Okay, but so now the obvious question, why? Why should this be the volume formula? It's not really intuitive why it needs to be that way. So I want to just give you an argument for prisms. The argument for cylinders is similar, but it's not really worth dwelling on all the details. I just want you guys to have intuition. What's important to me is that you don't know oh my gosh, more spelling errors. Okay, now I think what I've written here is correct. Sorry, there we go. It's just like normal class, am I right? Nothing's changed. Okay, right. So I don't need you guys to know rigorously how all this stuff works because you guys are teaching, but I do think you guys should have intuition so that when you're teaching, you can remind yourself, yes, these things are right and stuff like that. So let's try to find the volume of this guy. Let's figure out how many 1 inch by 1 inch by 1 inch cubes fit in this prism. Okay. So I've got a width of 2, a length of 3, and a height of 4. And my goal is going to be to try to figure out how this formula for area of the base times height gives me this formula. And for this, I'm actually going to switch back to a video again. Let me just do that. All right, we're back. So here is my prism, right? This should have like the same dimensions. It's if I treat these side lengths as inches, this is 2 inches, this is 3 inches, and this is 4 inches. You can see that, right? 1, 2, 1, 2, 3, 1, 2, 3, 4. So this basically has the same proportions as that object you see in the notes. And so the point is, why is the formula base times height? So first of all, let's do a quick sanity check. I've already shown you this object. We counted by hand that there were 24. It took me 2 tries, but we got it eventually. There were 24, right? I went through and I counted everything. So let's see if the formula we have in the notes are right. I'm pointing like this because the notes are behind me on my computer screen. So sorry if that's a little jarring. Okay, so do we get 24 using the formula? Well, we have the height. The height of this is 4 inches because here are my 2 bases, top and bottom, and the height is the distance from the bottom base to the top base. So 1, 2, 3, 4. There's the height. Okay. And area of the base, well, if I just flip over and just look at the base, I see that I have a 2 by 3 rectangle, which conveniently is also something we've already talked about, but it doesn't matter. We already know how to compute areas for rectangles. It's just length times width. And so this is 3 times 2 is 6. So area of the base is 6, height is 4. Volume for this should be 6 times 4, which is 24, which is what we got just by counting the cubes, which is right. So why did that work? Why did this formula make sense? Well, notice I can break up my prism along the height so that I'm going to break it up into layers so that each layer has a height of 1. Okay, so how many layers do I have? I have 4 because the height is 4 and I broke up each layer into having a length of 1 height. So I will have height many pieces. right? So now let me put down these extra pieces and let's just talk about one. Now I want to talk about how many cubes are in just one layer, because all these layers have the same dimensions. So if I can figure out how many cubes are in one, I can figure it out in all of them with the same reasoning. And how many cubes are in here? Well, there's only one layer, so I can just look at the side view. And when you look at the side view, oh wait, we just talked about this. This is literally just a rectangle now. I can forget that this is a three-dimensional object now because there's only one layer. And I can count the number of cubes here by just counting how many, just by counting the area of the base, by seeing how many squares are in this rectangle, which of course there are 6. So each layer has 6 cubes because the area of the base is 6. So area of the base gives me the number of squares in each layer, because each layer is basically a copy of my base. Okay, so area of the base tells us how many cubes are in each layer. So how many cubes do we have total? Well, I know I've got 6 in each layer. Let's think about this as groups. I've got how many groups of size 6? Well, I've got 4 layers, so it should be 4 groups of 6, and multiplication tells us that 4 groups of 6, that means we've got 24 cubes in total. It's 6 times 4. That's how we define multiplication with groups. So where is the height? Well, the height is the number of groups. So the size of our groups is the area of the base. That tells us how many cubes are in each group. We have heights many groups because if I break up along the height into one length things, I get that many layers, that many groups. So that's the reasoning for that. So it's pretty cool, I think. So in the notes, I basically did an overview of this. So let's go back to the notes. All right. So I've basically documented what we did. I broke up each layer into 4 layers, and then I took this top layer and I said, well, look how many cubes are in it. I can look at the top, and so I can figure out how many cubes are inside of it, and then use group multiplication to justify the volume formula, right? And so that's basically it. I'm just going to write it down more formally. The number of 1 by 1 by 1 cubes in each layer is the area of the base. The number of layers is the height. And so we get height times area of base, which is 4 times 2 times 3, which is 4 times 6. And the reasoning for cylinders is the same. Obviously, with a cylinder, you've got a circular base, and with like triangular prisms, you have a triangle base, but the idea is the same. You break up your object into so many layers, and then the number of unit cubes that fit in it is the same as the area as the base. So that's the intuition. Okay, so this all makes sense if I have like right prisms and right cylinders, but what if I have oblique prisms? And this is where shearing comes in. Remember, if the height is like this for a right cylinder, for example, when I shear, this height is going to stay the same because all I'm doing when I shear is I'm going to pull everything horizontally, and all of these slices will shift over little by little to get this more slided object. But the height will still be the same. So we won't change the height, and the base is obviously still the same. And so this all works out by shearing. We're not going to really dwell too much on oblique prisms and oblique cylinders and stuff like this, but just know that the same formula works because of Cavalieri's Oops, that's not a highlighter. Cavaliere's principle. If you remember when we shared area or two-dimensional objects, area stayed the same, so the same happens here. All right, so that's enough of me talking. I'm going to pause here and say, I hope I'm probably over-explaining some things. It's really, really hard. I did not anticipate the difficulty of not being able to read everybody's faces. That is a big challenge of doing things this way, but I'm hoping it's still okay. And at the very least, if I've explained myself into confusion, you can come ask me questions about it. Anyways, here's a problem. This is where I would like you to pause your video and try to find the volume of these shapes. I will say B should be a little bit easier than A. I kind of came up with A first, which is why they're labeled the way they are, but give them a try. So go ahead and pause the video now. Spend 5 minutes on this. All right. Hopefully you paused. Hopefully you were honest. Let's do B first since it's a little bit nicer. So remember the formula for volumes is just base times height, area of the base times height. So let's just work this out in detail. Area of base, I've got a 1 meter base, so the radius, oh yeah, I guess I should have said you should assume it's a circle, but we're always going to assume these things are circles in this class. So pi r squared is the area for a circle. So in this case, pi times 1 squared is just going to be pi meter squared. Okay, so that's the area of the base. Height is 4 meters. And so the volume is 4 times pi. And what are our units? Units are really important. Remember, we ended up excusing you guys for the units on that one mastery quiz. So now you've got to show us, you know, that we're using cubic units. Okay, that one's not too bad. One thing I will point out that I think is nice to know is notice here we've got meter squared and here we've got metered. And if I multiply meters by meter squared, we get meter cubed, which makes sense. That's kind of how multiplication works with variables. So I think that's valuable to notice. All right, that's B. Let's do A. A is a little more complicated. What you have to be able to see is you've actually got 2 prisms in here. You've got a rectangular prism here, and then you've got a triangular prism here. But it doesn't matter because for cylinders and for prisms, the formula is always base times height. So starting with the prism, so I'm going to call this shape A, and I'm going to call the pyramid B. So the height of A, so notice the height here is the height here is the height here. Okay, so all those heights were meant to be seen as the same. So the height is 2 meters. The area of the base, well, I've got a 10 by 3, so I've got 30 meters squared. And so volume A is 2 times 30, which equals 60 meters cubed. Okay, and now we do the same thing, but for B. The height of B is still 2 meters. The area of the base, well, notice I've got a 4. And notice this distance over here is 3, so that distance is 3. So what that means is that I have 1/2 the base of that triangle, which we'll call 3, times the height, which is 4, okay? So this may be hard to see, so I'm just gonna like right here draw what you see the reason the base and the height are 3 and 4 is that this was a right triangle. If you look, you can see I have little perpendicular marks, which I neglected to tell you when I started. My apologies. I hope you saw those right angles there. Maybe I'll make a note of that. Right triangles. Okay. Cool. So that's the area of the base because we know how to find areas of triangles. And so the volume, volume B equals area of the base, which I'd never finished, but it's 1/2 3 times 4, which is 6 meters squared. So it's 2 times 6, which equals 12 meters cubed. Okay, let me just make sure we're doing everything right so far. Three times 4, yep, divided by 2 is 6, and then we multiply by the height. Good. All right, so I found the area, I found the volume of these two prisms. The point now is that the total. So the adding and moving principles for areas is the same for volumes. If I've got two volumes side by side, then their total volume, as long as they're not overlapping, is just the combined amount. It's volume A plus volume B. Which is 60 plus 12, which is 72 meters cubed. And there we go. That's how to use the volume formula to find volumes. All right, let's talk about volumes for pyramids and cones now. So the volume formula for pyramids and cones is kind of going to be similar. So we still need to establish what the height is. The height for a pyramid or cone is the distance from the apex down to the base. So here I've done it for this one. And it's that vertical distance. So you could also think about the height as a distance from this center point down to the center of the base. So that's also the height. So those two heights that I've labeled, those are the same things. They're just, one's just shifted over. And the same here, I can take this height down from here to there. And again, I can also just take the vertical distance down to the, those are both the same lengths, is really what I'm trying to explain there. Okay, so the volumes for pyramids and cones ends up being actually really similar. So we've got a little bit of a spoiler on the screen, but that's fine. So you still take the height and you multiply it by the area of the base. But this time you take a third of that volume. That's the volume. So it's like the area. So you should notice this is like the area for a prism or a cylinder with the same height and base, but then you scale it all by a factor of 1/3. So the question is, why is it 1/3? And I have a, we're not gonna get into the details of this as much as we did for the prism, but I think the visual here is like really freaking cool, and it's worth you guys seeing. So we're gonna pause and do yet another video. Okay, a little bit weirder of a setup here, but gonna have to be what it is. So I've got some shapes here. I've got an open-faced cube, and I've got 3 oblique looking pyramids, right? So they're pyramid. Why are they pyramids? They've got a polygon base, and then they all come together at the apex. And it's oblique because this apex isn't right above the center, right? Here's the center, and it's over here. So I've got 3 pyramids. They all have the same dimensions for their base. They're all these squares. They're all the same. And they all have the same height as well, if you notice. They're all standing. It might actually be a little confusing because of the perspective. Let me try to make sure there. You should be convinced here. Yes, they are all the same height. Remember, the height is this distance from the bottom to the top. So this right here, the eraser to my top of my index finger is the height of these, okay? And I'll point out this cube has the same height as these and the same base. Okay, so what am I gonna do? So notice I've got 3 prisms here, and I'm gonna put the base of this prism, I'm gonna put it in this cube so that it hits the base of this. So I'm gonna put it inside like that, nice and snug, and there's still some space in there. And so I'm gonna use these other 2 pyramids to fill in the blank space. Here we go. So I put in my second one, and already you're starting to notice it's starting to actually fill. Sorry, the lighting's a little tricky, but I think you guys see it. All right, and now for the last one. Now notice when I put in this third one, I've actually filled in the cube entirely. So what does this mean? That means the volume of these 3 pyramids that I just stuffed in here, 3 pyramids, they're all the same size, so they all have the same volume. The 3 of them combined have the same volume of this cube because I literally could squeeze all 3 inside, right? Okay, well, what's the volume of this cube? Well, the volume of cubes, well, cubes are just, they're prisms, right? They've got 2 bases. They've got a bottom base and a top base, and they're pyramids. Or I'm sorry, they're prisms. So they're just prisms with a square base and where the height is the same length as the length on the base, right? So the volume of this cube is the area of the base times the height by our formula. Okay, so now let me take out my pyramids again. Here are my pyramids. They still kind of look like a cube. So now, if I combine the total volume of these 3, I know their combined volume is the area of the base, which is the same as the cube, times the height, which is also the same as the cube. So now I can forget the cube was even here. And so if I want to find the volume for just one of them, well, since they all have the same volume, I have 3 groups, each with the same size. That means the size of just one of them is the total divided by how many groups I have, which in this case is 3. So I have 1/3 of the area of the base times the height, which is exactly what we have in our notes, which I think is pretty cool. All right. So I hope it was like a little enlightening. Like, again, my goal here is not for you to like have a rigorous argument, but I want you to just have the intuition. And I think it's kind of cool that you can fit this 1/3 here really means that I can fit 3 pyramids inside of a prism. And the same logic will work for a cone, but that's not so important. I want you guys to practice using these. Before we do, let's talk about the volume for a sphere. So here, I'm just going to give you the volume. It's 4/3 pi r squared. I do not want to dwell on the details here because it's not going to be very important. You should know the formula exists and that it looks like this. And the reason you should believe this formula is right is notice this cross section here of the sphere that I've drawn. That's a circle. And that has area pi r squared. And you can see the pi, and we have 2 r's right here. So where's the other r coming from? Well, one thing I'll comment on is this is a cubic volume, so we should expect a cube somewhere. Where is that 4/3 coming from? Well, the 1/3 is actually coming from this formula. You can actually use a cone to find the volume. And what you end up proving is that in half of a sphere, so in like this half of a semisphere, you can fit 2 cones, which have which gives you a 2/3, and then you have 2 hemispheres, so that gives you 2/3 plus 2/3, which is 4/3. So that's like the basic idea of where the formula comes from, is you can use cones to get the volume for a sphere. So now that we have the volume for all these objects, I just want to take a brief moment to compare and contrast volume and surface areas for three-dimensional objects. And what I want to say is kind of analogous to what we said about perimeters and areas for two-dimensional objects. So in the two-dimensional world, if this is my object, the perimeter is this outside piece, right? The stuff along the outside. And the area is all of this stuff on the inside. For three-dimensional shapes, it's actually the exact same idea. The surface area is how much cloth you would use to cover the outside, for example. Or maybe if you had a gift, you can think about this as wrapping paper. On a gift. Right? It's how much you put on the outside of the surface. It's how much makes up the surface of the object. The volume is the stuff that goes inside of that object. It's what fills up the space inside. So in my gift analogy, it would be how much stuff you can put in the box. Okay, so perimeter is outside, area is inside of the shape. For two-dimensional, and then for three-dimensional stuff, the surface area is like the outside and the volume is the inside space. Okay, great. Now let's do some problems. So I was originally going to make these problems for you guys to pause and do, but especially with the extra videos I'm doing and because I'm not really scripting everything, I think the video has been a little bit longer than I anticipated. So you're welcome if you feel that you have the time and it benefits you, you're welcome to pause and do each of the following problems on your own. But I'm not going to be as clear cut that you do that. Okay, so here's the first problem. We start with a prism and it has a square base with side lengths of 4 centimeters. So here's a little representation of our picture. Let me try to get dashed lines right. So we've got a prism like so. And the base is a square, so it's 4 centimeters by 4 centimeters. And we filled it up a third of the way with 100 milliliters of something, of water. So I'm imagining like it looks like this, right? So what do I mean by a third of the way? That might be unclear. So notice right now, we haven't said anything about the height of this prism. And in fact, the problem is asking us, what is the container's total volume? So right now, I don't actually know how tall this prism is. So I'm just going to say the height. I'm just going to make an arbitrary decision and call it h. Okay. So the prism is 1/3 full. What does that really mean? That means this height right here, from the top of the surface of the water to the bottom. And let me make this more like what it should look like. So how high up is that water? Well, notice the only direction I can be filling in this is going upward. So if I'm 1/3 of the way full, then the height of the water in this prism should be 1/3 h. Take a moment and convince yourself of that. If it's a third of the way full and the height is h, then the height of the water should be a third of h. Okay, so the goal here is to find the volume, and I know volume is area of base times height. So the area of base is easy to compute. It's a square base, so it's 4 times 4, which is 16. The height Well, we actually don't know the height, it's h. And we weren't given any information about the h. Instead, we were given some information that if I fill it a third of the way, then it's containing 100 milliliters. So somehow we have to figure out how to get the height given that extra information. And notice that I can actually extract the water as its own tinier rectangular prism, right? So one property we're using here is that water takes the shape of the container it fits in. And that shouldn't be anything mind-blowing, right? You've filled up bottles of water all your life and watched water take the shape of the object you're using. So what are the dimensions of this? So this is supposed to be, this new picture I'm drawing is supposed to be like the block of, some block of water that's inside that container. So I'm like kind of extracting it now. And the dimensions of the base should be the same because it's in that container. And what's the dimension of the height? Well, up here, the height of the water was a third of h, because a third of the water, because we filled up this big container with a third of the way with water. So this is right here, 1/3 h. Okay, cool. So the volume. So maybe I can't say anything about the volume of this prism just yet, but the volume of the water is easy to compute in terms of h. It's the area of the base times the height. Okay, well, why is that useful? Well, this is where we're going to do something that's a little bit tricky. The fact is that this volume of water corresponds to the same amount of space as 100 milliliters. So look back up here. We have 100 milliliters of water, and that 100 milliliters is what's being put inside here. Now, don't forget, milliliters is a capacity, not a volume. So technically speaking, this equation that I'm writing right now is like complete ludicrousness and baloney, and it's like, what the heck am I doing? This side is volume, this side is capacity. Those aren't the same things. However, in this case, it's reasonable to be associating the volume to the capacity and saying that this much volume represents this much capacity. This makes sense because if, for instance, if I tripled the amount of water, if I got 300 milliliters, it would make sense that that would fill up the entire container, because 100 is just a third of the container, and so 300 is the whole container. So somehow the volume of the whole container corresponds to the capacity of the whole container, and that's why this equal sign is okay. For those of you that have taken 101, we're really talking about proportional things. They're directly proportional to each other. If I double the water, if I double the capacity, I double the volume, and so on and so forth. So this is a heavy loaded equality sign, and this equation that I just wrote is responsible for why capacities and volumes get confused all the time. So just know that they're different, but in this case, I can write this equal sign because the space that they represent, this cube represents 16 times 1/3 over h volume, and it also represents 100 milliliters of water. So we can set this up and solve for h. So doing this gives us 100 times 3 over 16, because, we multiply both sides by 3, and then we divide by 16. And so as a result, we get 18.75. And so the height of the container is 18.75. And so what's the volume? Well, the volume of the water is, so remember we're asking for the total volume of the container. So we now found the height of the container. Sorry, I'm going a little fast. Let me back up. So this height right here, so this h we found was the height of the original container. And so now we can take 16 and multiply by 18.75 to get a total of 300 centimeters cubed. Okay, cool. Let's keep going. That's the first problem. Second problem is a little more involved. There are 3 parts. So we've got a cylindrically shaped pool with a circle as its base. And the area and the radius of the base is 15 feet. And the height is 10 feet. So it's a little shorter than it is wide. It's actually a lot shorter, but that's fine. Not a big deal. All right. And we're told that this shape is filled to the top with water. So we're imagining we filled it all the way up. All right? So what's the volume of the pool? In other words, how much water volume is inside of this? So this is a pretty quick computation because we know that volume is just area of the base times the height. So this is 2,250 pi. Oh yeah, and of course the units are feet cubed. Okay. That's all there is for part A. There's not too much going on here. All right, the water is transferred to a pool with radius 20 feet. How high would the water be? Okay, so this is a little bit trickier now. So now we've got a new pool. It's a little bit wider. And we're not really given how high up the pool is, but just intuitively speaking, notice the radius of this pool up here was 15 feet. It's now 20 feet. It's wider. So if the pool is wider, you should expect the height of the water to drop. So just for the sake of a drawing, I'm gonna draw it like this, like as if we can see where the water stops in the pool. And I'm going to label this height of where it stops as h. So this should look like that first problem we did together in this part of the notes. Okay, so how high is the water here? Well, we can find the volume of the water because the volume of the water right now, it's sitting in a cylindrical container. So the volume formula for the water, it's taking on the shape of a cylinder. We should use the cylinder formula, which is area of the base, which is 20 squared pi, times the height, which is the unknown that we're looking for. And that's what's going to equal what? So right now, that is the volume of the water. But we actually know how much water we put in this pool, because that's the same water that was filling up this pool up here, the water that had a radius of 2,250 cubic feet. So this volume right here that I just wrote down, this actually equals 2,250 pi. And so we can solve for h pretty easily from here. And we end up with 5.625 feet. That's the answer. So the work involved in this problem, I don't think is actually that bad. I think it's pretty easy when it comes down to the algebra. But I think what's not easy and what is actually kind of challenging is knowing how to use the formulas we've talked about to solve these problems, right? All I did so far was talk about formulas, but these are like And I bet you were probably expecting something like compute the volume of this. These are a little bit more challenging, but I think they're still doable. You just kind of have to use a little bit of reasoning to figure them out. And I'm hoping that doing these problems will help you with that. Okay, so quick sanity check, by the way. This pool has, in this pool, the water goes up 10 feet, right? And this one, it only goes up 5.6 feet. What's the difference in these two pools? Well, one's wider, right? And if it's wider, you would expect the water to not need to go as high. So this 5.26 feet right here, that actually makes sense. I should expect the water to be lower because the pool is wider. Okay, and quick comment. Hopefully I was being clear when I said this is easy. I wasn't really saying the problem itself was easy. I'm just saying that I think this work, there isn't too much involved. That's all I really meant by that comment. Okay. All right, cool. So we have part A, we have part B. Let's go on to part C. Now we have a new pool. This time the pool has a triangular prism as its base. And it's actually a right triangle. That's kind of like what it looks like. And the point is I fill this up with water, so I got my colors all mixed up. So there's the water, and we've now transferred the water into this pool, and now the question is, how high up is the water? So that's H for the height, and it's the exact same process now. We know that the volume of the water, we already know it's 2,250 pi cubic feet from part A, but also right now the water is taking on a new shape. It's now taking on the shape of a triangular prism. The area or the volume of a prism is the height times the area of the base. In this case, we have a triangle. Triangles have a base 1/2, base times height. It's a right triangle, so the base and the height are the lengths that I gave you, right? All right, and we can solve for h from here. Half of 40 is 20, so I get 600h equals 2,250 pi. And so I can just solve for h. Whoa. 2,250 pi divided by 600. So if I was looking for an exact answer, the answer I would give is 3.75 pi. But if you want an approximate answer so that you can compare this to parts A and B, it's approximately 11.8 feet. Okay, so that means it's actually a little bit taller than the first example. In the first example, it only went up 10 feet, but in this example down here, it went up 11.8 feet. What you can gather from this is that the area of this base right here is probably smaller than the one in part A, and you can check that. All right. On to the last one. All right, this one just looks pretty straightforward just at a glance. It's a cone. We need to find the volume. And sorry, there's a radius thing right there. There we go. And that's not too bad because we have a formula, right? It's 1/3 area of the base times the height. So just at a first glance, this doesn't look like too tedious of a task until you realize we're not actually given the height. This height is missing. Again, kind of like as I've already warned you guys, this length right here, that's like the slant length. It's not really the height. It just tells us how long the sides are. So I have the base. I can find the area. That's easy because it's a circle. But how do I find this height? So look at this, look at it some more, and your eyes should start flashing a triangle at you. The height that goes from the apex to the center, and then from the center following the radius to the outside of the circle, and then going up along the 5-inch side, we've got a right triangle. The height needs to go straight down, so it needs to be perpendicular to the base. And so what we've just deduced is that the sum of the squares of the two sides, h squared plus 3 squared equals 5 squared, because it's a right triangle. Pythagorean theorem tells us how to find h. So we get 25 minus 9, h equals plus or minus square root of 16, which equals plus or minus 4. And of course, having a negative height would be blasphemy. And so the answer is 1/3 area of the base, which is pi radius squared times the height, which we just found is 4. And we end up with 12 pi cubic inches. That's it. So this problem ended up just like the other ones. I don't think the actual algebra involved is ever like too gross or too intense. I think there are just like some clever and tricky things that you kind of need to see once or twice. And I think with all 3 of the examples I've done, this should get you in a good position to do all these homework problems. Of course, you shouldn't hesitate to ask for any help. Okay, so I hope this is clear and this was okay. You shouldn't hesitate to ask me any questions if you were like, I don't get this explanation you gave at this part. But yeah, all right. Hope this was helpful. Hope this was an okay and successful first class. I think this video ended up coming out a little bit longer. I forgot to start a timer, so I don't have any reference. But yeah, if you have any suggestions, do let me know. And otherwise, we'll chat again in the next class, if not in some online office hour. See you all later.